Hello guys, welcome back for the UGC lecture series on laser physics under Swayam portal. I have given few lectures on different aspects of lasers. Now for the last from 1960 up to 2024, almost for 64 years old, this technology. This has a wide range of applications. It has dominated the world, in particular in science and technology. For example, the 5G communication, which you all enjoy in your house using Wi-Fi, strongly depends on variety of application in lasers in microcircuit preparation and bringing messages and feeding into the optical fiber. Just I am giving two extreme examples. Another one, some time ago, there was a space vehicle which went up to Mars or which went up to Moon, and if you want to see what are the composition of the Moon soil or Mars soil, there is only one way. You send a laser beam, high power laser beam, so that it falls on the soil, burns the soil, produce vapor, and then you can put your camera straight, focus on that one, then get the image. From the image, you can have a reasonably good understanding of what are the elements and the compounds present in a Moon or on a Mars soil. You see, there is such a wide range of applications of laser. Okay. Now, based on so many applications, because of the variety, because of the what you call versatility of the lasers, there are so many lasers available, and they can be classified in different fashion: gas lasers, liquid lasers, solid state lasers, pulse laser, continuous wave lasers. And then among themselves, you can have ultra fast lasers or secondary lasers. Ultra fast laser, one example is a femtosecond laser. Another example of a secondary laser is a Raman laser, which means you start with the high power neodymium laser, put a Raman medium like a benzene, which I like very much. I mean, it's not I like benzene much. Benzene is a very poisonous liquid, remember. I start with the neodymium laser, put a benzene in between, then it will produce a laser from the benzene based on the Raman effect. Such a laser is called Raman laser, and they are called a secondary laser because to produce a laser of different color, wide range of colors, we start with the high power laser. So, high power laser acts as a primary laser to produce laser from the secondary laser. Another example is harmonic generation, frequency conversion. There are so many things. Now, I will not be able to go into the detail all of them. For our level of understanding, for your level of understanding, I would divide all these lasers which I have been discussing into two categories. One, a 3-level laser which will give always pulsed output, and a 4-level laser which will give a continuous laser output. How do you say 3-level? Why 4-level? To show the difference and the importance of 4-level laser, we had to revert back to a little theory. We will work out what are the rate equations which govern the population inversion in different energy level of a medium. That is the purpose of this today's talk, and we will just go into the detail. I will be explaining as best as I can, and there are certain equations which you have to work it out all by yourself. Let us go into this one. As I told you, we employ a certain set of rate equations to understand the population density as a function of time at different energy levels of atoms or molecule. That is the purpose of today's talk. Why do we do that one? Only then you will gain about the insights into the nature of the pump energy, nature of the output laser. Both will be able to be properly understood only when you have a certain theoretical understanding of population inversion in different energy levels. Let us consider two-level atomic system. Just imagine I'll just give the example. Yes, look at this diagram. I have got two energy levels, E1 and E2. In fact, at the beginning, when Einstein worked out, he started only with this. Same way, when we started the lecture, I started only these two energy levels. Let us go back and see how we build population inversion and what kind of laser we can get out of this one, if at all. Whether we can get or not, we will come to know in a short while. Let us imagine there are two energy levels, E1, E2. Whether it is a gas or a liquid or a solid doesn't matter now. For us, there is some medium, it has got two energy levels, E1 and E2. Now, under this condition, we are going to produce population inversion, try to get laser action. Let us see some basic theory out of this one. Now, look at this one. We have written down the rate equations for the population density in each energy level. dN by dt represents the, we have already defined what is N, what is delta N, what is W12, what is W21, all of them are defined below. Let me explain what it is. N1T plus N2T represent N. What does it mean? It means N1 is a population density, which means number of atoms per unit volume in that particular energy level 1. N2 represents the population density in the level 2. Why we put subscript in the bracket T? Both are functions of time. In any case, N1 plus N2 should be equal to N, which is the total number of atoms per unit volume in the container which we have taken. Since we have got a closed enclosure, closed system, N does not run away. So, atoms should be either in N1 or in N2. Because of this one, N1 plus N2 is equal to N. Delta N represents the energy level difference between N1 and N2. N1 is a ground level, it will be very high. Population in N1 will be very high. N2 will be population in energy level 2. So, delta N represents the difference between the population between N1 and N2. When you have a population inversion, the delta N will be minus because N2 will be bigger than N1. We will see all those things later. Next point. Omega 1, 2 represent the deactivation rate or emptying rate of atoms from level 1 to 2. Same way, W21 represent emptying or refilling of energy level 1 by the atom coming from 2 to 1. What that means is, suppose I excite atom from E1 to E2, then by stimulated emission, N1 will be emptied slowly. Then N2 will be populated, but N2 cannot stay there for a long time. So, it will just drop by spontaneous emission atoms back into N1. So, that rate both put together represents 1 over T1. That means that is the lifetime of the level E1. We will use a very similar definition For E2 also, I have explained everything. In this case, only important is N0 equal N10 minus 20, which represents the population difference at thermal equilibrium condition. Note also, W12 will be equal to W21. That means the rate at which one getting emptied should be equal to rate at which it gets refilled, because there are only two energy levels. In the two state energy level, if N0 should be greater than 0, then W12 should be, it is something related to the excitation energy or input signal which kicks the atom from energy level 1 to energy level 2, and it should be very strong. Only then you will have W12 greater than 0. From the above equation, you can easily see that with the two energy level, it is not at all possible to produce population inversion, because whatever is taken up will come down. Because to come down, you don't need any energy. They come down spontaneously. Since there are two energy level, you kick it up more, they will come down. Kick it up more, come down. So, population inversion is not possible with only two energy level. So, let us forget this one. Let us go to the next step. Let us try three-level system. Examples for three-level systems are already we have discussed earlier. One such example is a ruby laser. Let us focus all our attention on this kind of ruby laser, which is a classical example for three-level system. Let us see the picture. Now look at this one. You have E1, E2, E3. Now when we try to pump it using a flash lamp, intense flash lamp, ions, chromium ion of ruby laser will get excited from E1 to E3. That E3 is called the pump level, because it is at this level ions are put into taking from E1. Ions are kicked from E1 to E3 by the pump. So, the top level is called the pump level. Then what happens? From E3, those ions come down to E2 by non-radiative transition, and it is very fast non-radiative transition, and the time it spends is called T32, because that is a time of atoms to come down from E3 to E2. Okay, next one. T21 represents the time that atoms take to come down from E2 to E1. E2 represents the higher energy level or upper laser level. E1 represents the lower level, which is the ground level. This is the constriction, this is the limitation of three-level laser. Let me repeat. In a three-level laser, like ruby laser, ground level is same as a lower laser level. E3 is the pump level and E2 is upper laser level. This is how it has been defined, this is how they operate. This is not what I like it. This is how ruby laser works it. Next one, since it is behaving like this one, I have to develop an equation, develop a design according to what the material I have taken for laser action. Okay. Now, W13 is the emptying rate from 1 to 3, and W31 represents the emptying rate from 3 to 1. This should be equal to WP, where WP represents the pumping rate. What we mean by pumping rate is, I kick the ion from E1 to E3. Suppose I kick them at 1000 ions per second, 1000 ions will go, but remember the same radiation will be able to kick number of ions from E3 to E1 also. So, the pump rate will be same for transition 1 to 3 and 3 to 1, that you can understand. With this situation, let us now write down the rate equations for each energy level. Now, look at this one, dN3 by dt, which means the rate change of population in the level 3 is equal to Wp, which is the pump rate, multiplied by N1 minus N3, that is population build up in N3. N3 divided by T, 32 represents the rate of transfer of ions from 3 to level 2. Now, it is very clear, that is how the ion behave in level 3. Now, come down to upper laser level, which is the N2, dN2 divided by dt, that is the rate change of population in N2 is equal to N3 T32, that is N3 divided by T32, that is the number of ions which are there in upper or pump level, and the rate is inverse of T32. So, this is how atoms or ions are brought from upper pump level to upper laser level, minus N2 divided by T21. T21 is the lifetime of the ion in upper laser level. So, this is how it decays. It can decay spontaneously, it can decay by stimulated emission also. So, it is a total decay rate. In a molecule like dye molecule or a gas like this one, imagine that you have built sufficient number of atoms in upper laser level. They can come down to lower laser level by spontaneous emission, by stimulated emission, and they can come down by collision with the wall, collision with other atoms also, because they will be running around. Such a thing will not take place in the case of solid, because atoms cannot move around, ions cannot move around. They kept fixed in a solid. In any case, we just generally say N2 divided by time T21 represents the decay rate of upper laser level. Now, next we have the equation N, the total number of ion, is equal to N1 plus N2 plus N3. What we mean is, look at it, it is a total closed system. So, the ions should be either in N1 or in N2 or in N3. They cannot run away. So, that is the equation. Next one, we define another parameter beta, which is N3 divided by N2. N3 is a population in pump level, N2 is a population in the upper laser level. You define it, this is just equal to the transition time or the T32 divided by T21. This is the, already we have defined it, this ratio can be easily checked, that is defined as the beta. With this, we go back to the equation, put them all together, and then we try to simplify that exercise. We leave it with you. We have no time to go through all the steps. Under this condition, N2 minus N1 is a population inversion divided by total N. N is a total population, or that means the fraction of population inversion, that is the meaning of this one. The fraction of population inversion, or let me put it another way, suppose we have taken only 100 ions for our laser process. N2 minus N1 may be 10, N will be 100, that means only 10 ions are there in the upper laser level. The population difference is only 10. This is equal to, I can put all this equation 1 minus beta WP T2 1 minus 1. You can work it out. Now, in this case, it is easy to see if we assume that the atom at E3 decay to E2 immediately, that is very fast. Usually it is, because already we have seen the ruby laser, the radiative decay time is of the order of, it's a non-radiative decay time of the order of picosecond, whereas the lifetime in the upper laser level is of the order of 3 millisecond. 3 millisecond is very, very high compared to picosecond or a nanosecond. Under this condition, that beta can be 0, then under this condition we can simplify the population inversion density, or the percentage of population inversion density is given by the equation WPT21 minus 1 divided by WPT21 plus 1. This means this equation easily shows very crucial point. The left hand side, there could be significant population inversion provided WP is really, really high. If we can pump it very hard, not only that, if decay time, if the pumping rate is bigger than, I mean, if you can pump it hard such that energy, the time decay from 2 to 1 is reasonably higher, in that case you can get a population inversion, then you can get a laser action. For a ruby laser, T2 to 1, that is, I go back to show what is T2 to 1, this time is 3 millisecond. 3 millisecond is a very, very, very large time in these days of laser. You can get a laser from 3 nanosecond laser media, for example, for a dye, for a rhodamin 6G dye, the lifetime T21 is only 3 nanosecond. Here it is 3 millisecond, nanosecond, millisecond. This is 1 million times slow. It is very, very, very slow. Since it is very slow, we were able to pump it not so hot, and still we were able to get population inversion, and that is the reason one Mayman was able to get the laser action from ruby, because that was a primitive stage. We were able to get all this one because of this one specific condition with which he carefully designed and chose this one. Okay, now let us go to the 4-level laser. The 4-level laser, there are many examples. The most important example is helium-ion laser, which I touched upon, and the last to tell you the design aspect. Another one is neodymium laser. These are the most popular lasers throughout the world. The neodymium laser has a 4-level. You can look at this one: N1, N2, N3, N4. N4 is a pump level. You use a flash lamp, put lot of light to raise the neodymium ion from E1 to top level, which is the pump level. Then from the pump level, rapid decay is written there. That means the ions transfer to very quickly to upper laser level. That is a E3 level. From there, they come down to lower laser level, producing spontaneous emission, stimulated emission. Not only that, there is some problem. The light emitted can always be absorbed, so this E3 level may be reabsorbed. That's called self-absorption. That also is possible. Apart from that, from N2, there is a transition to the ground level. This is also a very rapid decay time. Now, to get a CW laser, you should have population inversion always positive. That is, N3 should be greater than N2. This is possible. After working with all these one, you will see that this is possible at all only if T43, only T32, that is the time of transition from E3 to E2 is much greater than the transition time from T21, that is transition from lower laser level to ground level. That means the lower level should be empty. If the lower level is empty very fast, you will always see that there is a population inversion, that is you will have ions in the upper laser level, that is N3 minus N2 is always positive. There is substantial population inversion, then you can get a continuous laser action. This is an essential condition for CW laser action, and that condition is satisfied in neodymium mag laser. For example, for neodymium mag laser, this time T32 is about 200 microsecond. On the other hand, T21 is about 200 nanosecond. You see, the lower laser level get emptied 1000 times faster than the upper laser level, which means it will be almost always empty. When it is empty, population inversion can be easily built up. That is the reason why neodymium mag laser is a very successful laser, very efficient laser, more successful than the ruby laser. Nowadays, ruby laser is almost always forgotten. It is the museum piece, even though that was the first one to make it. In summary, what we need is this. I would sum up the difference between 3-level laser and 4-level laser by this diagram. Look at it. On the x-axis we have normalized pump rate, that is 1 unit of pump or a second unit of pump, third unit of pump, just one step. You can say 1 kilowatt or 100 kilowatt, 200 kilowatt, 300 kilowatt. Then you will see N, which represents greater population inversion, is positive, which means for a 4-level laser, even in a low level of pumping rate, you can have population inversion. So laser action starts almost from the beginning and continues all the beginning and keeps on growing as you pump it more. In contrast, in 3-level laser like ruby laser, you need enormous number of pump levels so that you have at least 51% of the atoms are there in the upper laser level and only 49 are there in the lower laser level. That means the input energy is very high, the output is not so high. Because of this one, 3-level laser like YAG laser, ruby laser is very inefficient. Same thing is true for nitrogen laser, same thing is true for excimer laser. All these lasers are pulse laser, first thing, very inefficient, but they have their own application. In fact, excimer laser is the most favored laser. Nitrogen is my favorite child laser. Each one has its own application in spite of that low efficiency. The best is always neodymium YAG laser. That is the most loved, wanted laser. I have been able to give the essential feature of why certain lasers are very useful, very much loved. Neodymium mag laser, dye lasers and the semiconductor lasers are the most versatile, most loved, most respected lasers. With this, I would sum up this point. What you have learned today, particularly in the population inversion rate equations, is why certain lasers are very efficient, why certain lasers are inefficient. That comes from the nature of the medium. Remember, it is the nature of the medium which determines the major properties of any kind of design, of any kind of successful operation of any device. Thank you very much.